Let's do some practice over rational exponents and exponential functions. 6-2, find the indicated real nth roots of a. So this means that we are doing the sixth root of 64. And what I'm going to do is write 64. And I know that that is like 8 times 8, but since I'm looking for the sixth root, I'm going to break this thing down into its factors like this. And so that means I have 1, 2, 3, 4, 5, 6. Well, hey, look at that. 64 is 2 to the 6th power. So so the answer is 2, okay? So when I'm doing, like a reminder, if I'm doing square roots, I'd be looking for couples. But I'm not looking for a square root. I'm looking for a sixth root, which basically means I'm looking for a team with 6 individuals. And oh, look, this one has exactly one group, one team of the 6 identical individuals, and it's a 2. Over here, the fifth root of 243. So just like the last one, I'm going to break it down like this. I'm going to see the smallest things that can go into it. And by smallest things, I mean prime numbers, right? So let's see, I have 1, 2, 3, 4, 5. Okay, well, again, I don't know my 5th power items, but 3 to the 5th power, hang on, I shouldn't write it like that. 243 equals 3 to the 5th power, so the 5th root of 3 to the 5th is just 3. Next, find the dimensions of the cube, check your answer. The volume is 729. Okay, well, so a cube, just so you know, is going to be this side times this side times this side. That's how volume works, is it's 3 dimensions. So essentially, you're just doing the cube root of 729. So similar to the last few, I'm going to divide it by stuff I know. And by the way, the first thing I get is 243, and it's like, oh, look, 243. So this is essentially going to be 6 3s. So it's 3, and then I'm going to write it like this. And I'm going to also write it like this, just because maybe it will help some of your brains to see it a little bit better. I could just divide that by 3 and get 2. So that means I would have 2 groups of 3, and so that's 9. Or if you want to look at it this way, oh, look, there's a group of 3, it goes out. There's another group of 3, it goes out. And that's 3 times 3, which is 9. So number 3 is 9. Number 4, it's 10. Okay, so if it's 1,000, the cube root of 1,000 is 10 times 10 times 10. Thousands are awesome because you don't have to think a whole lot. Moving on, number 5. Evaluate the expression. So the cube root of negative 512. We can do this because it's going to be negative something times negative something times negative something. And a negative times a negative times a negative gives you a negative. Now, be careful, there's this other negative outside. So our final answer is going to be positive because of both of those being negative. All right, so 512, that's divisible by 2. So that's 256. That's 128. That's 64. And then did we do 64 a second ago? 64 is 2 to the 6th. So check this out. This guy is 2 to the 6th. In fact, you know what? I'll just keep going to make a little bit more sense visually. How about that? So what happens is we have 1. So 64 is 2 to the 6th. 1, 2, 3, 4, 5, 6. And now 7, 8, 9. So what's happening is this is the negative cube root of negative, and I'm going to leave that negative outside, 2 to the 9th. Okay? So we can divide that 9 by 3. And what that means is it's 8. Why is it 8? Because one 2 is going to go out, another 2 is going to go out, and a third 2 is going to go out. So the answer is just 8. Now, it would have been -8 if it had only been this blue part. But when they throw in that red negative, that's why I mentioned that our final answer was going to be positive. So it's 8, all right? 729 to the 1/6 power. Well, guess what? That's the 6th root of 729, okay? So let's divide it. Wait, do we have 729 already? We did. 729 is 3 to the 6th power. Okay, cool. So this problem is really fast then. 6 is 3 to the 6th power. Wait, it was 3, right? Yeah, 3. So we divide that by 6. It's just 3. That's it. 3 to the 6th. Take the 6th root, you get 3. This one is no solution. Why? Because we cannot take an even root like that of a negative number. Now, you will learn eventually that you can still calculate it, but for right now, it's just no solution. And that's the explanation, is we can't do an even root. Okay. Write in rational exponent form. So key here is exponential form, okay? So what I'm going to do is -53. I'm just going to leave him inside a parenthesis. And I'm going to deal with this radical. That's to the 1/5 power. And then I'm going to put this guy who's outside of the whole thing to the 4th power. And then I'm going to combine my powers. That sounded fun to say. Combine my powers. It's -53 to the 4/5 power. Very similar here. We're going to take 110. We're going to raise it to the 1/4 power. We're going to raise that to the 7th power. And we get 110 to the 7/4 power. Now we're going to write them in radical form. They're in exponential form. We're going to do radical form. So there's a couple different answers we could do, and I will attempt to do both. So -34 is being raised to the 4th power, which is also being raised to the 1/9 power. So you have this as an option. You could have -34 to the 4th power inside of a 9th root. That is one possible answer, okay? And the other is you could have it like this. You could have -34 to the 1/9 power, which has the 4th, to the 4th power outside of that. So it would look like this, -34, the 9th root of that, all raised to the 4th power. That's the other possible answer there. And if you're like, well, what's the difference? It's really just how you approach it. Those are both the same answer, okay? Or they would end up at the same answer. An ugly one, right? Okay. 41, same idea, 41 to the 1/4 power raised to the 7th power. Well, you could write it like this. You could write it like this. The 4th root of 41 raised to the 7th power. That's one answer. The other is 41 to the 7th power to the 1/4 power, and you would get 41 to the 7th power, the 4th root. And here I'm going to erase the 7. It feels a little like it's not raised to the 7th power. Now it does. Okay. Evaluate the expressions. Okay, so basically what we're doing is what we did here, but making it a little bit more complex because the exponents are just, well, the exponents are more complex. So -1, well, hang on. Can we do this? Yes, because our root, that's 1/7, and that's odd, right? And we can do odd. So what I'm going to do is actually, let's see if I can take 128 and divide it by 2, and I get 64. Wait a second. We know this from doing this over here, that 2 to the 6th is 64, so guess what? 2 to the 7th is 128. So check this out. What we can do is negative 128 to the 1/7 power raised to the 3rd power. Well, this red part, I know I just underlined it green and said this red part is negative 2. How? Because the 7th root of 128 is 2, okay? And it would be negative because if you multiply something by itself, if you multiply something negative by itself 7 times, you will get a negative answer, okay? And then the last part is cubed. So negative 2 cubed is negative 8. Now, what if we'd done it the other way around? Well, you would have had to have cubed 128 and then taken the 7th root of that. And the idea is that 8 to the 7th power is whatever that would have been. And that's pretty ugly. I don't know what 8 to the 7th, but here I got the calculator. 8 to the 7th power, only 2,972,152. No big deal, right? Okay, cool. So that's the kind of thing we're after here is look for the gimme part, the easy part. Like when I look at this, I think I can't do it, actually. Because I can't take a square root of negative 25. So I'm going to go with no solution. Yeah, you can't do that. Okay, number 14. We have 1,000 to the 1/3 power. We did that right here with this cube, and it was 10. So 10, I'm kind of cheating, and not cheating, I'm kind of going a little bit ahead of myself and not even dealing with the 4 yet, but it's 10 to the 4th. Well, guess what? That's 10,000. I mean, 1,000, so here, 10 to the first power is 10, 10 to the second power is 100, 10 to the third power is 1,000, 10 to the fourth, 10,000. Done. Slide over here. So 125 to the 1/3 power. I'd rather deal with that first and then square it because I know that 5 times 5 times 5 is 125. So 5 cubed is 125, and the cube root of something cubed is just that thing. So this is 1/5 squared. This is 1/25. And if you're like, well, this seems weird, why are we doing this? Really, we're just following exponential like rules and seeing if we can navigate. Why would you actually do this? There's probably, I don't have a great answer for you, other than it's kind of fun puzzle solving, if you ask me. Okay, 343. We dealt with 343. No, we dealt with 243. But if I remember, 343 is 7 cubed. Let me verify that on the calculator. 7 cubed, 343. So check this out. First, we got our first negative exponent. So what we can do with that is this. Like that. And then this is now just the cube root of 1/343, which is the cube root of 1/7 cubed, which is just 1/7. So, not too crazy. 17, 1/64th. We're taking the square root of it, which is the 1/2 power, by the way. The square root of 1/8 is, I'm sorry, I said the answer. Square root of 1/64th is 1/8. And then you cube that. And again, I'm squinting. This is 1/512. 8 to the third power is 512. The other way of doing this would have been you had to have cubed 64 and then taken the square root of it, and that would have been really gross. The radius of a sphere is given by the equation, the radius of the sphere is given by the equation that, where V is the volume of the sphere. Find the radius to the nearest centimeter of a sphere that is a volume Okay, so they're giving us things. Volume, 268. And then use 3.14 for pi. Okay. And we're supposed to be finding the radius. We want that. Okay, radius equals 268. 3 times 268 over 4 times 3.14, all cube rooted. Well, I gotta be honest, I'm grabbing a calculator. I recommend you do too. 3 times 268. I mean, I guess we could, if we wanted to, we could do some canceling here. You know, for example, like 2 can go into that, and this is 130 to 134. I mean, but that's not that great. You know what I'm saying? I don't want to do that much work. I mean, I guess here we'll do 3 times 134. That's 402 over 2 times 3.14 is 6.28. I guess I should have known that. And to the 1/3 power, we're going to need a calculator for this, because when it comes to decimals, we're just not. We know square roots as exhibited by all this on whole numbers. We're not so much with the things like that. So really, I grabbed a calculator and I'm going to type in 402 divided by 6.28, and I'm going to raise it to the 1/3 power, and I get 4.000265375. So I'm just going to say that the radius is 4. Okay. To calculate annual inflation rate, R in decimal form, of an item that increases in value from P to F over a period of n years. This is one thing I like and hate about math, is we can do all of this stuff, and now we get some like semi-application stuff. I don't know if this is real or not. Let's check it out though. So find the annual inflation rate to the nearest 0.1% of a rare coin that increases in value from 0.25 to $1.50. So we know where does that go versus where does that go. Well, check this out. From P to F over a period of n years. There's 30, so that's n. This is easy peasy. We got this. So R equals $1.50 over 25 raised to the 1/30 power minus 1. And if you're thinking you don't want a calculator, if you're going to just brute force this thing, bro, you're going to take the 30th root here. Not me. I'm grabbing my calculator. In fact, I'm just going to pause the video so you don't have to listen to me type it in. Here we go. So I typed all that in the calculator. I got that the rate equals 0.061544917. I'm sure there's more to it. So I'm fine if you leave it like that, but just know they're asking for the annual inflation rate. This is basically a percent then. So the rate equals 6.15%. And if you think about it, if you had a coin, something that was worth a quarter, over 30 years, if it grew by 6%, it'd get to $1.50, which you might think is like nothing, but hey, go ask anyone if they would take a 6% guaranteed return on their money over 30 years. That sounds okay to me. I don't know. It sounds better than a punch in the face. How about that? So, by the way, that is 6-2. Let's take a look at 6-3. Determine whether the equation represents an exponential function and then explain. So, number 1 is yes. Why is it an exponential function? Because it fits the form a times b to the x power, and b does not equal 1. So if you're like, I wonder what a and b are. A is actually -1, and b is 6. There you go. This is not exponential because b equals 1. And I did an example of this on the Big Ideas assignment, that if you were to pick x's and plug them in, here's what would happen. If you plugged in 0, 1 to the 0 is 1, and 1 times 5 is 5. And then if you were to do 1 to the first power, that's still 1, and 1 times 5 is 5. And if you do 1 to the second power, that's 1, and 1 times 5 is 5. Do you see a pattern here? 1 to the third power is 1, and 1 times 5 is 5. So it's clearly not exponential. It's actually linear. Over here, this is not exponential. So no, this is actually a cubic function. Cubic. And if you're like, is it because of that? Yeah, it is. Now, if it had looked like this, 7 times 3 to the x, then it would be yes, but it is no because it's cubic. Determine whether the table represents linear exponential, and then explain. So our x is going up by 1 each time. I like to see that. This is going down by 3, down by 3, down by 3. That's linear because it has a slope, a constant slope of -3. That's it. So how about this one again? The x's are going up by 1. I like that because it's just helpful to calculate. That is going down by 12, down by 6, down by 3. Or you could look at it as divide by 2, divide by 2, divide by 2. And if you're like, but wait, exponential functions aren't divided by 2. What about times 1/2, times 1/2, times 1/2? So yes, this is exponential because it has a rate of change of 1/2. I guess rate of change is not the right idea. Yeah, anyway, it looks like that. So when I say it looks like that, that was a little vague. It looks like that when it's exponential. It looks like this when it's linear. Evaluate the function for the given value of x. So we're just taking this guy and plugging him in here. 1.2 squared. Now on the big ideas assignment, I said something like, you really don't necessarily want to do the decimal stuff, but this one's not that bad. Like there was one where it was like using pi and it was like to the 30th root. That was insane. But this is just, okay, we can multiply 2 times 2 is 4. Actually, so 2, 4, 0, like that. 4, 4, 1. Move the decimal place twice. It's 1.44. 7. Oh, you know what? I just realized I could have made this a lot easier. That's just 12 times 12. And then move the decimal twice. Cool. Plug in -2 right here. 1/2 times 8 to the -2. That's really 1/2 times 1 over 8 squared, which is 1/2 times 1 over 64, and you multiply straight across, you get 1 over 128. Fun. Graph the function, compare the graph to the graph of the parent function, identify the y-intercepts, asymptotes, and find the domain and the range of f being the function. So here's what's up. Number 8 and number 9 are not moving left or right, up or down. So we can start with this, that 5 is our initial value, meaning when we plug in x is 0, so like if I did a table and I said x is 0, 1/4 to the 0 power is 1, and 1 times 5 is 5. So check it out. There's our y-intercept, or our initial value, right? And then now I kind of regret putting the 0 right here, just because you know me and like how I like to organize these things. So let me erase this a little bit, start again. The other thing I was thinking, other than organization, is this is exponential decay. How do I know it's decay? Because our A is there, our B is there. If B is between 0 and 1, that's decay. And 1/4 is definitely between 0 and 1. So the idea is that if I plug in -1, we're going to get 5 times 1/4 to the -1st, which is 5 times 4, which is 20. So check this out. Boom, right there. And then if we do 1, so 5 times 1/4 to the first power, which is 5/4, or 1.25. So boom. And it's going to approach our asymptote, which is 0. So it just kind of looks like this. There we go. Okay, now here's A is -1/3. So really, we can go ahead and put that in. -1/3 right there. And then again, I'm just going to do a table. X, Y, boom, 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 boom. 0 would be -1/3 times 3 to the 0 power, which is -1/3. Now this one is growth because our B here is bigger than 1. B is greater than 1, so that's growth. So let's plug in a 1, and we're going to get -1/3 times 3 to the first, which is just -1. So 1, -1. And if you're like, wait a second, this is growth because that appears to be going down. It is, but this negative has flipped it. So let's keep going, like 2. -1/3 times 3 squared. Well, that's -9/3, which is -3. So 2, -3. And then if we did 3, so that's -1/3 times 3 cubed. That's -1/3 times 27, which is -9. So at 3, it's -9. And then we could keep going, right? But let's not keep going, shall we? But if we went negative, so we would get -1/3 times 3 to the -1, which that's -1/3 times 1/3. That's -1/9. So now notice if this is 1/3, 1/9 is 1/3 of the way there. So it's awfully small, right? And so now we've kind of seen our asymptote is 0. So this is what this thing looks like. Really long, skinny, really close to 0. And then boom, crazy fast growth. Okay, so that is what that graph looks like. So we did this in our notes in class, or I think it was just one a lot like it. So here we go. We got A is our initial starting value, which would be -6. But hold up. We are going to move to the right 1, or +1, and then we're going to move down 4. So that's that purple dot, that's where we would have been, except that we're going to move to the right 1 and down 1, 2, 3, 4. That is where our initial value is now. And if you're like, but how is that the initial value if it's there? If it's there, right? Well, okay, let's do this. Let's do a little table. So let's do 0, okay? So plugging in 0 here, I'm gonna do it like right up here. -6 times 1/3, 0 minus 1 minus 4, yeah? -6 times 1/3 to the -1 minus 4. -6 times 3 minus 4. This is now -18 minus 4. That's -22. Okay, so when x is 0, y is -22? Dude, it doesn't even fit on our graph, really. It's down here-ish. Okay, so, oops, did I mess up? Should it not be -6? No. Now let's try 1. Okay, so back up here. If we do 1, so I'll do it over here. -6 times 1/3 to the 1 minus 1 minus 4. -6 times, well, that's 0, right? That would be 1. That's -6 minus 4 is -10. So check it out. Oh, by the way, I forgot my negative here. -22. So check it out. When x is 1, here's 1, right? What did we say? We would go down to -10. Nailed it, right? So that's a little trick to starting your initial value is that, hey, it would have been -6, but not anymore. It's moved over right down 4, okay? And then let's just do another couple points. Let's do a 2. So -6 times, now I'm going to speed this up a little bit, and that 2 minus 1 is 1, okay? -6 times 1/3 minus 4. -6 times 1/3 is -2 minus 4 is -6. So let's put in -6. And at 2, we got -6. Should we do one more? I guess we should do one more, right? 3. By the way, notice we didn't have to do any of that stuff. 3. I'll speed it up slightly more. So 1/3, it'll be squared, right? So that's 1/9. -6/9, which that's really -2/3, right? So that's -4 2/3. So, okay, we didn't get a pretty answer, and that's okay. You're not going to get all pretty answers necessarily, right? So at 3, -4 2/3. So, what do you notice that we are approaching? Because we're used to kind of approaching 0, right? Are we approaching 0 on this one? No, we are approaching -4. That is our asymptote. So technically speaking, you could put in like a dashed line. Why don't I do a dashed line? Dashed line, do I have a dash? There's a dashed line. Let's put that at -4. That's fun. So here we go. Let's graph this. It starts down here, it goes up, and it starts to really get flat. There's our graph. Okay? It's a decaying graph, but it's flipped upside down. The only reason I'm pointing that out is I pointed, stuff out like this over here. This was decaying regular. It started up, went down. This was growth, but flipped upside down because of that negative. Growth because of the 3, flipped upside down because of that negative. Over here, we are decaying because of 1/3, and it's flipped upside down. So imagine it was decaying, but it gets flipped, so it looks like this. And one more. We are growing, and there's no flip. So here's what we can do. This is our initial value of 2, but it will not be where we actually start. So we will not be at 2. That's where we would be, but we're going to move left 1. And if you're like, wait, why are we moving left? I'm still a little fuzzy on that. So this is the formula for an exponential function. This moves left and right. This moves up and down. And the idea is that by default, this is negative. So when you look right here, and that's negative, then what's going on? And that's positive, then what would you have had to have put here? A -1 to experience this +1, right? So that's what's going on there. I just ended up erasing all that. Cool. So we had our initial value. We're going to go left 1, and we're going to go down 3. And if you're like, why have you skipped the 5? It's not like we're going to put a 5 on the screen because of that 5. It just tells us that we are growing, that it's growth. When b is greater than 1, it's growth. So then what can we do with our funny little non-y-intercept, non-starting point? Well, we can move left 1 and down 3. So let's do that. Left 1 and down 1, 2, 3. There should be our starting point, and let's prove that if we can. So we'll do a table. X, Y, blah, 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 blah. So when we plug in 0, you'd think you would get that original 2, but you don't. You get 2 times 5 to the first power minus 3. That's 2 times 5, which is 10, minus 3 is 7. So check that out. We are here when that tells us we should be here, right? Oops. Or no, that's just how it works, because we said, remember, it's moved over and down. So what is it at -1? Well, let's do that. 2 times 5 to the 0 plus, not plus, minus 3 is 2 times 1 minus 3. That's -1. Check it out. That is at -1, -1. So we were right. Let's keep going. How about -2? 2 times 5 to the -1 power minus 3. That's 2 over 5 minus 3. That is -2 3/5. -2 3/5. Well, okay, -2 3/5. There-ish, yeah. And again, that tracks because our asymptote is -3. So let's go ahead and throw that dashed line on that -3 right there. So we will not hit that line. And if you're like, well, you sort of did right there. I mean, again, I'm not perfect in my drawing, but this is what we've got, is we've got a graph that will be very close to hitting -3. It hits that dot, it hits that dot, it hits that dot. Notice it doesn't hit that one because that was like our fake. We thought it was going to hit that, but it doesn't actually hit that. So see you later, other little dots. There is our graph like that. Okay. Compare the graphs, find the value for H or A. Okay. So let's see. This thing, our original F, has an initial value of -1. That makes sense based on what we're seeing there. This one, however, if we were to like follow this, maybe it's just 1, 2, 3. It just looks like it's moved over 3, so H equals 3. These are actually not too bad because mainly we can't ask too crazy of a question, and they kind of tell us they're telegraphing. They're like, hey, you're gonna find an H, okay, and H only moves left or right. You know what I'm saying? And A, now A says that we're going to change the starting value, the initial value. So the initial value here is 1. How do I know that? Because there's nothing else there, right? Nothing there. So this starts at 1, as it does. But this one starts at 4, so A must be 4. Compare the graph of f of x equals 2 to the x to the graph of g of x equals 2 to the x minus 3. How are the y-intercept domain and range affected by the transformation? So the y here was what I'm going to do. I'm going to split them. And this is blue. This is green. The y-int is 1. The y-int is not 1. So here's what I'm going to do is I'm actually going to graph it and be like, hey, this one was 1, but this one gets moved to the right 3. So all I have to do is go 1, 2, 3. It's right there. So really, actually, I don't know the y-intercept. I would have to plug in 0. So when I started doing this, I guess I just kind of reminded myself that's not going to help me with the y-intercept. But it's good to know that you're off. So this is where this right here is where the y-intercept will be. You plug in 0 for x, 2 to the -3rd power. That is 1 over 2 cubed, which is 1/8. Okay. The domain is going to be all real numbers. The domain is going to be all real numbers. The range is going to be y is greater than 0. The range is y is going to be greater than 0. So how we've compared them, how the y-intercept, domain, and range affected. Boom, that was it. And if you're like, wait, I'm not really sure how that works. So here's the blue graph. Here's the green graph. It's just moved over. So as I look at this, all the x values will be the same on both. Well, the y values will be the same on both. And if you're like, what do you mean the same? I mean that if I plug in a 2, I will get a value. Now there'll be different locations. And if I plug in a 50 billion, I will get something. If I plug in a negative 50 billion, I'll get something. So there you go. So we did it. We did it. That is rational exponents and exponential functions. That's 4 pages of math. Had such a good time. Let me know what questions you got. See ya.